Welcome to another Algebra 2 video. Today we're going to talk about polynomials and their roots. So let's start by defining what we mean by polynomial. What is a polynomial? Well, if you've been watching my videos previously and followed along with this series, you've actually already seen lots and lots of polynomials. Put simply, a polynomial is just a string of letters and numbers multiplied and added together. Let me give you an example. Here's the most basic example. Well, 2x. That's considered a polynomial in a way. It's a number times a variable. Not a very useful one, or at least not a very exciting one, but technically a polynomial. Now, something like this, also a polynomial. I can add more terms to this. I can do something like this. That's also a polynomial because I have letters and numbers and powers of letters added or subtracted together. We can even do more than this. We can do something like this. And I could do this all day, lots of examples. But the point is, any string of numbers and letters added and multiplied together, we consider a polynomial. Okay? Now, this one in the middle, you've seen a whole lot of. That's a very special case. We call that a quadratic. And we spent a whole series of videos talking about those, and it's going to be very useful to us soon. But in this context, we just kind of call it a polynomial. Now, within this term polynomial, we can specify more sizes. What I mean by that is, these terms look different, right? Even though they're just strings of numbers and letters, and they're all the same, in that regard, they are different sizes. So we are going to be able to define them based on that. So for instance, this one here only has one piece. It has two things in it, but as far as adding and subtracting, there's only one thing, right? This has 2 here and then 3 and 4, as you see. But this one we're going to call, because it has one piece, we're going to call it a monomial. Okay? And that comes from, obviously, mono, which means one. So this one, having 2 pieces, we're going to call a binomial. Of course, because bi means 2. Now, following that name convention, you could probably guess what the next one's going to be. Trinomial. And it's called a trinomial because it has 3 pieces. Now, we called it a quadratic before, right? And that's still true. But let's be very clear here. We called it a quadratic because it had a square in it, right? And its highest power was a square, right? So that's what made it a quadratic, not the fact that it had 3 pieces. So while this is a quadratic, because it's a square, it's also a trinomial because it has 3 parts to it. And you could have quadratics that didn't have 3 parts to it, right? They wouldn't be trinomials. We could have binomial quadratics, things like that. Anyway, I don't want to get too bogged down into that. I just wanted to make sure that was clear that this is both a trinomial and quadratic, but we're dealing with different characteristics, right? Okay. Now, after we get past trinomial and we have 4 or more pieces, like say this one down here, it's got 4 pieces. Once we get larger than 3, we stop counting. I mean, there are terms for it, but we really don't use them most of the time. So we just say, in general, these are going to be just polynomials. Okay, so anything larger than 3 pieces, we just say it's a polynomial. Now, to be clear, all of these are polynomials, whether it has 1, 2, 3, 4, 10,000, infinite number of pieces. It doesn't matter. They're all polynomials. It's just that we have special names for, one that has a 1 piece, 2 pieces, or 3 pieces. Okay, I think that's enough said about that. There's also something else we should talk about before we get into the math, terminology-wise, and that's something called degree. Let me get rid of some of this stuff here. Oh, that was a 1, not a line. All right. So the degree of a polynomial Very easy to define. It's just the highest power you see. Let me actually write that out for you. The degree is just the highest power. And we also call it the order of the polynomial. So to go back to our friend the quadratic, the highest power is 2. That means it has a degree of 2. This polynomial down here, it has a highest power of 3, so its degree is 3. Now it has other x's in it. There's a square here, there's a power of 1 here, but none of those matter. All that we care about when we're looking at the degree is the highest number. Now if you look at something like this one, this binomial here, the highest power it has, well, it doesn't have an exponent, but you can imagine there's a 1 right there because that's just x to the first power. So this is a degree 1 polynomial. Okay. All right. I don't want to drive that into the ground too much because that's not too difficult, right? So whatever the highest power is, that's the degree. And you can, some people will try to trick you and mix these things up. So it's not always the first one. They might put the highest power later on in the polynomial. You just make sure that when you're looking at these to find the degree, be careful and actually pick the highest number. Okay, I think that's enough terminology. I think we're ready to go and dive into roots of these things. And to do that, let's go back to our friend, the quadratic. So let's go back to an example, or a type of example that we would have seen previously. Let's do something like this. Now, if you've watched the quadratic videos, you will have done many of these, and we found the roots of these, but I want to remind you of the definition of a root and how to find them and things in this context, because we're going to start to expand that concept to larger ones, right? Things with degree 3, degree 4, and beyond. Okay? So let's think back to what we did before. What we did was we said that our roots are going to be places where our graph crosses the x-axis, at least most of the time. And when we get into complex numbers and imaginary numbers and things like that, it gets more complicated. But in general, it's going to be where it crosses the x-axis. Okay, so let's suppose that my graph crosses, say, like this. Oh, something like that. All right. Now, notice where this thing crosses. If I were to look at the coordinate here, it's some x coordinate, but the y coordinate is going to be 0. It has to be 0, right? Because it's on the x-axis. That's the whole idea. And same thing here. It's some x value. I don't know what it is yet. That's what the root is. But the y is going to be 0, right? That's the whole idea behind a root or a 0 or an x-intercept. Okay, so this number here is the root. And we know that it's a root because when you look at the graph, it crosses the x-axis, or when you plug it into this function and it gives you a y, it's going to be 0. Okay, and that's the way we defined it before. Now, we also learned how to find the roots of quadratics. How did we do that? Well, most of the time, if possible, you want to factor. And this one is factorable. That's the way I designed it. So let's factor this thing. So if I factor it, I'm looking for two numbers that multiply to give me this last number. So they're going to multiply to give me negative 24. But they're going to add to give me that middle number. So the two numbers that multiply to give me negative 24 but add to give me 2 are, of course, going to be 6 and negative 4. Now, quick side note, if you are not comfortable with factoring, or you've forgotten, or you don't have enough practice, I highly suggest going back and watching my factoring video, or watching anybody's factoring video. Go back and practice factoring. Find some practice and do lots and lots and lots of these, because as we go through this polynomial unit, I'm going to assume that you are very comfortable with this process. Okay, it's going to make your life a whole lot easier if you're very comfortable with it. Okay, anyway, so let's talk about how we actually define these, or how we actually find these roots. And remember, I said that if you plug them in, they're going to give you 0. So the way we did it was we said, all right, let's make it 0. So if this function is forced to be 0, what would these x's have to be? Right? Now notice I have two things multiplied together. They are called factors for that reason. I have factored, and factors are things that are multiplied together, right? So we say I have factored it because I have a piece here and a piece here multiplied together. Now, if I have two numbers multiplied together and the result is going to be 0, what do you know about those numbers? Well, if you think about it for just a second, you know that one of them has to be 0. That's the only way you can multiply to get a 0, right? So this is either going to be 0, this thing, or this thing is going to be 0. That's how that works. Okay. All right. So take a second and think about it. What would I have to plug in to this number to make it 0, to make this whole piece 0? Well, if I plug in a -6, -6 plus 6 here will give me 0. This whole piece is 0, right? Which means no matter what this is, it's 0 times whatever that is, that's going to give you 0, right? That's how we did our roots before. And the same thing goes for this piece. What number would I plug in to this x to make this piece go away and become 0? Well, quite obviously, 4, right? 4 minus 4 is 0. This thing is now 0, which means whatever this is, it doesn't matter. 0 times that mess, which in this case is 10, will give me 0. Okay. All right. Now, I hope I didn't go through that too much or too deep. I'm not trying to overdo this, but I want to remind you the process and why it works. Okay. So basically what we did was the shortcut was if you swap these signs, you end up getting the roots, right? So the roots are -6 and 4. And I'm actually going to fill those in here. Okay. So this is how we found the roots of quadratics. Now, just because I had to factor it to find that doesn't mean that it stops being a root in this form. That was probably a poor way to say that. Let me explain what I mean. Let's say someone already told you that 4 was a root of this, okay? And let's say you didn't factor it, or you did factor it. Either way, but you wanted to prove that 4 was a root of this. Let me get rid of all this stuff. Let me show you what I mean. So, to be clear, I want you to show that 4 is a root of this thing. So those are the instructions. So how would I show that 4 is a root? Well, you could either find it, right, by factoring it, or you could do what defines the root, and that is plug it in and see if it equals 0. So let's actually do that. So to show something as a root, all I really have to do is plug it in everywhere you see an x, and then see what happens. So let's do that. 4 squared, 16. 2 times 4 is 8, minus 24. 16 plus 8, 24, minus 24. Look at that. In fact, it gives us 0. That's so cool. I've done a million of these things, but I don't know. It just still excites me when this stuff actually works out like it's supposed to. Anyway, so to show that something is a root, you can either find it, right, by factoring it and actually calculating what the root is, or you can just plug it in and verify that it is in fact 0. Now, if I plug in any other number, and this is worth noting, if I plug in any other number that's not a root, it's not going to give me 0. Now, let me actually show you that. So if I ask, is 2 a root of this polynomial? And we already know it's not, but let's say you didn't know. How do you find that? Well, let's plug it in. That's how you do that. So 2 squared plus 2 times 2 minus 24. That's 4 plus 4 minus 24. That's 8 minus 24. And what is that? Negative 16. Is negative 16 0? No. Negative 16 is not 0. So we say 2 is not a root of this polynomial. In fact, or this specifically this quadratic. Okay. All right. So in the case of quadratics like this, it's easy to find the roots. You just factor it. And if you can't factor it, remember you can use the quadratic formula. That will always work. All right. But to test whether it's a root, you can plug it in, and if it's 0, it's a root. If it's not 0, it's not a root. Very simple test. So now let's go to something larger. And that's kind of the point of this video. So we're going to take that concept and we're going to extend it. So I'm going to give you a larger polynomial. Something like this. Now the question is, how do we find the roots of this thing? Well, sadly, we're not actually going to get into that in this video because it's going to take more tools, more techniques, and we are going to do that in a few videos from now. But what we can do now is we can test whether numbers are roots or not in something like this. Finding them is going to be, as you'll see, a little bit more involved than just factoring like we just did with that quadratic. So again, we're not going to find it, but we can test it. Now, before we do that, it might be worth noting or worth knowing how many roots this thing has to begin with. So wouldn't it be great if we had a way to do that? Well, it turns out we do. So how many roots does this have? Well, remember when we talked about that thing called the degree? What is the degree of this polynomial? Well, the degree of this polynomial is just the highest power you see, right? That's the 3. Well, it turns out that whatever your degree is, that's how many roots you have. So if I have a degree 3 polynomial, then I have 3 roots. Now, to be very clear, especially when we go way further into this, you may not always be able to find those 3 roots. They might not even be like graphable. They might be imaginary or something weird, but they do exist. There are 3 roots. And this is such an important fact that it is called the Fundamental Theorem of Algebra. Let me actually write that down. That's worth writing. This is the fundamental, oh, that doesn't look like a U, fundamental theorem of algebra. That doesn't look like theorem. Let me try to write a little better. Theorem of algebra. Okay. This fact that the degree of your polynomial is also the number of roots you have is so important to mathematics as a whole that it has earned itself the fundamental theorem title. It is the most important result of all of algebra. Now, you may not think so. It may not seem like that big a deal. It's like, okay, it's not hard, a hard concept to wrap your head around. It makes life easier. But as you get further in mathematics, especially the higher you go, you realize how far-reaching the implications of this fact, in fact, are. It's very, very powerful. Okay, so all this says, again, the fundamental theorem says that the degree, this is a very mathematical way to write this, of the polynomial is the same as the number of roots. Okay, now if you look this up in the textbook, it's going to be a whole lot of words and a whole lot of letters and numbers and variables, and it's going to look really, really confusing. I like to do things in a more intuitive way. That's why I make these videos the way I do. So I want you to just understand the application of it. So whatever the degree is, that's the number of roots. Okay, so we have 3 roots. Let me get rid of my definition. So we've determined that this has 3 roots. What are the roots? We do not know. Now, I know because reasons that I'm not going to go into right now. I'm going to go ahead and tell you what they are. I'm going to show you what we can do with them. All right. Again, we're going to find them later. But right now, let's just play with them. So the roots are, of this polynomial, 2, -3, and -1. So remember the definition of a root. A root is a number such that when I plug it in, I get 0 out. So if you were asked to show that 2, for instance, is a root of this polynomial, all you need to do is plug in 2 into that polynomial and test it. So for my students, I will ask questions on homework, tests, whatever. I will ask you to show that a particular number is a root. And what I'm asking you to do is to plug that number in and show me with your work that you in fact, verify that it gives you 0. Let's do that. So I'm going to plug in 2. I'm going to verify or show that 2 is a root of this. So everywhere I see an x, oh, that's not plus, it's minus. Everywhere I see x, I'm going to plug in a 2. All right, let's work this out. 2 cubed, that's 2 times 2 times 2, 8. Now here, I'm going to do the exponent first. So 2 times 2 is 4. And then times that 2 out front is also 8. And this is a negative 5 times 2. That is negative 10 and minus 6. Now be careful with these things, order of operations and all that stuff. When you get to a string of just addition and subtraction, it's usually best, if you're not good with how these work, is just to go left to right. So this is 8 plus 8, which is 16, minus 10 minus 6, and that gives me 0. So look, we have verified that 2 is in fact a root. So if you wanted to write that out, we would say 2 is a root. And we know that because when we plugged it in, we got 0. Now, I said and wrote up here that there are in fact 3 roots to this thing. So any of these 3 numbers plugged in will give you 0. Let's do another one to practice the algebra. Actually, tell you what, you do this one. I want you to pause the video and plug in the other 2 and verify that you get 0. It's also good if you're not fast at manipulating these things. It's good practice to plug these numbers in. So go ahead and pause the video, plug in -3, plug in -1, and verify that these do in fact give you 0. And if they don't give you 0, look at your work and try to figure out what you did, and then come back and I'll show you how to do it. Okay, here we go. So I'm going to plug in -3. I'm assuming you've already tried this. -3 cubed. Oh, I do need to slow down a little bit so I can write better. Okay, the first term, -3 cubed, students often have a problem with this. When you have a negative number that's cubed, remember that's -3 times -3, which gives you a positive, and then times another -3. That's going to end up with a negative number. So 3 times 3 times 3, 27. So it gives you a -27. Something else that I see a lot of times people forget, they know, but when you don't have much practice with it, sometimes we forget that when you do terms like this, you have to do the exponent first, right? So 3 times 3, -3 times -3 is +9, times 2 is +18. And now I have a -5 times a -3, which is a +15, and then -6. All right, let's work left to right. -27 plus 18 is -9, plus 15 minus 6. Let's see, that's -9 plus 15 minus 6. Well, let me do it this way. 15 minus 6 is 9, right? And -9 plus 9 gives me 0. So I have verified that -3 is in fact a root. Okay. Now, it also works with -1. I trust that you've tried that and in fact got 0. I'm not going to go through that one with you as well. Now, it is worth going through the exercise too to show that any other number that you plug in is not going to give you 0. That is guaranteed. These are the only 3 numbers that will give you 0. They are unique in that way. So, for instance, let's pick a different number. Let's pick the number, let's make it quick. Let's make, let's ask the question, is 4 a root? Now, we already know it's not because we've already written 3 down. But let's say you didn't know what these 3 roots were, and someone said, hey, is 4 a root of this thing? And you'd say, I don't know. I don't know what the roots are yet. Let's pretend. Well, you would plug them in and find out. So let's do it real quick. Actually, this is a really good exercise for you to do, just to get good at plugging numbers in. I'd suggest pausing it, plugging it in, and seeing if you get the same number. Okay, here we go. So 4 times 4 times 4, that is 64. This is 4 squared, which is 16, then times 2, which is going to be 32, minus 20, minus 6. All right, that gives me 64 plus 32, that's 96. minus 20 and minus 6, that's going to give me, what is that, 70? Well, 70 is definitely not equal to 0, is it? So we are going to say that 4 is not a root of this polynomial. All right? And in fact, that will be the case with absolutely every number you plug into this, except for these three numbers. We know there are three roots because the fundamental theorem told me that because it's degree 3, there are three. And since I already know that these three work, nothing else will work. Anything else you plug in will not give you 0. And if you do get 0, you did something wrong. Okay? Okay, now this works whether it has degree 3, degree 4, degree 5, and on and on and on and on. Okay, and again, we're not going to find the roots in this video. I just want to show you how to test to see if it is a root, and get practice plugging them in. And what we can do, what we can extend this to in this video, is going backwards. Now let's say, for instance, you know that you have two roots. You have the roots 5 and negative 3. You don't know how you know that, or someone just gives it to you, or whatever reason, it doesn't matter. You know that there is a polynomial that exists that has two roots and two roots only, and they are 5 and negative 3. And you are asked to write a polynomial with those roots. How would you do that? Well, it's very, very simple if you just think about how we got roots like this to begin with. Remember, with our quadratic, we just swapped the sign. The logic behind it was a little more complex, but the application was very simple. We just swapped the sign. So to write the polynomial, you don't have to label it, but I am going to do that. That's not how you spell that. Polynomial. I'm just going to reverse the process. So I'm going to say x minus 5. Man, I cannot write. Slow down. And x plus 3. Okay? Now, this is what would have given me roots 5 and negative 3, right? Because we would have swapped the signs to get those roots. So to go backwards, to get the polynomial, I simply swap them back. Now, it's worth noting, some of you guys might have some questions right now, because you're like, wait a minute. At the beginning of the video, you said a polynomial was a string of x's and powers and numbers all added together, and this doesn't look like those polynomials. You are correct. This is still a polynomial. This is just factored. Okay, this is the factored form. All right, because it has been factored. How do we know it's been factored? It's because this is multiplied by this. It's only things multiplied, and these are called factors. And when you have factors multiplied together, it is factored form. So it is still a polynomial. It is just the factored form of a polynomial. What we saw before, when I first defined what a polynomial was a specific example, or a specific type, and that is standard form. That's when it's all multiplied out, right? So let's actually convert this to standard form. Let me write that down. So to convert to standard form, man, slow down and write better. Convert to standard form. That's the form we saw earlier, where there's no parentheses, right? It's all multiplied out. They're both polynomials, okay? They're different forms. Well, how do we do that? We just FOIL, right? Now, I hate using the term FOIL because it only works when you have two things times two things, technically, but I like to say distribute, right? So what we do is, to remind you, we go x times x and x times 3. That gives me x squared and 3x. And then negative 5 times x and negative 5 times 3 gives me negative 15. Right? And then remember, we would go down here and we would simplify this by taking these two pieces and adding them together. So we get negative 2x and minus 15. This is the standard form of the polynomial. Okay? So let's recap. You were given two roots. Someone said, hey, there's a polynomial and it has two roots and only two roots, and this is them. Can you write a polynomial that would give me these roots? So yeah, sure. So you write these down. This is the factored form, right? And if you're just given the factored form, you can stop here, or asked to find the factored form, you just stop here. If you were asked to give it in standard form, you have to multiply it out and go all the way down to this last step. Okay, all called polynomials, just different forms. All right, let's do another one like that, very simple one. All right, so we have roots. I'm going to start abbreviating things. Roots of 2 and negative 7. You try this one real quick. Write a polynomial in factored form and then standard form with these roots. Okay, here we go. It's actually really, really simple. You swap it. You know that if there is a root of 2, you have a factor of x minus 2. That's a good way to put that, and it's something that I'm going to use a lot in the future. You know that if you have a root of negative 7, then you have a factor of x plus 7. This is the factored form of the polynomial because it is factored. It is comprised of only factors. Now, if I'm asked to convert it to standard form, if and only if I'm asked to convert it, you don't want to convert it unless you're asked to, right? Because that's just extra work. Then you'd multiply. Now, I do want to talk about a shortcut to multiplying this out. FOIL technically has 4 pieces. You have 1, 2, and then 3, and then 4, right? But I'd like you to consider the shortcut that if this is just an x to the 1 and x to the 1, and these both look like these binomials here, and they both look like this, where it's x plus or minus a number and x plus or minus a number, you can skip one of those, right? So you can actually do this factoring, or excuse me, this multiplication by just going, well, it's going to be x squared all the time. If I add these two together, I get 5, so that's my middle term, and then if I multiply them, I get negative 14. It always works because that's how we factor to begin with, right? We ask what multiplies to give me this and adds to give me this. And that's how we get these. So why not use that in the forward direction, right? So just kind of a tip, a pro tip, if you will. If your binomials are simple like this and they both have degree 1, then you can FOIL very, very quickly. Let me give you an example. This is just a side note. We are done with the problem. Let's practice this. Let's say you're given x plus 5 and x plus 8, and you're asked to FOIL that out. Most students would multiply the way you're supposed to, x times both of them and 5 times both, and do all the whole, one of my students calls it the rainbow method, because you got these arcs. But in this case, x to the first and x to the first, you can just simply add and multiply. So that gives me x squared. 5 plus 8 is 13, and then 5 times 8 is 40. So when I do these in the future in the videos, I'm going to skip the middle step. I'm going to skip straight to this because I'm going to, 1, assume that you're good at FOIL, and 2, I'm going to be employing this trick, okay? This little shortcut. It's worth knowing. It's worth practicing. But also be very careful because it doesn't work if one of these is different, right? So they say that's an x squared or something. But in all the ones like this, it's going to be fine. So just another example real fast. I don't want to get too deep in the weeds, but I'm so excited about this trick that it's worth talking about. So if you were to do this one real fast, it would just be x squared plus 6x, and then minus 40. Done. I didn't have to do that middle step. I just did it in my head and did that. So that's a quick way to do that. All right. Okay, let's talk about how we would do it with larger degree polynomials. Let's say you're given roots of negative 5, negative 4, and 2. This is going to be a little different, isn't it? Now, we know from the fundamental theorem of algebra, if I have 3 roots, this is end up being a degree 3 polynomial. So let's do the same exact process we just did. Same thing, just with 3. So if I have a root of negative 5, I have a factor of x plus 5. If I have a root of -4, I know that I had to have had a factor of x plus 4. And same thing with this, and x minus 2. Now, if you're asked, again, to find the factored form of the polynomial, you're done. Congratulations. If you were asked to put this into standard form, you're going to have to do a little work, and we're going to practice that work. We're going to do it because, one, it's good for you, and two, I don't know, it's just good for you. It's like mathematical vegetables. Something is nobody likes doing this, but it's good for you. I promise. All right, so how do we do this? Well, what I'm going to do, I like to do is take the second two pieces and start with those. I'm going to leave the first one alone. I'm just going to multiply the second two. So I'm going to go down here. I'm going to write down the first term by itself. Just leave it alone. And then I'm going to multiply the second two. Remember that trick I just showed you a minute ago? I'm going to use it. This is x squared plus 2x minus 8. Now, if you don't like that, FOIL it out. Use the full method of multiplication of binomials. Please do that. But for the sake of efficiency and laziness and time, I'm going to do it that way. Now, this is partially factored. I'm going to call this, I don't think that's an official term. It's technically just factored, but I'm going to call this partially factored form because this is not fully factored, right? It's kind of a halfway step. This is not standard form yet, is it? Because I still have these things multiplied together like this. It's still technically factored. So we're going to have to keep going with this, aren't we? So how do we do that? Well, we do it this way, by distributing. So I didn't do a video on multiplying polynomials, and this is why. I feel like it's very natural to fold in the concept of multiplying polynomials into this lesson because you have to do it anyway. So just to multiply things of higher order, or more pieces, I should say, I'm just going to do it 3 times. So x times all 3 of those. Let's do that. So x times x squared is going to give me x to the third. Now x times 2x, that's going to give me 2x squared. And now x times -8 gives me -8x. So I've now used the first term. And now I'm going to work with the second one. It's the same exact thing as you would do with, the simple quadratics. But you have an extra term there. Now I'm going to do 5 times x squared. That's a positive 5x squared. 5 times 2x, that's 10x. And now 5 times -8, that is -40. This looks like a lot of work. And if you're not used to it, and you don't have a lot of practice, then it is. It's going to feel like a chore. It's going to be rough. But I promise you, if you do a whole lot of these and you practice them a lot, you'll get really good at it, and it's not going to be that big a deal. All right? The goal of this is to do as many of these as you can until it doesn't feel like a chore. Because it shouldn't look like a lot by the time you get good at it. All right, so now what we're going to do is combine like terms. So I'm going to look and see how many cubes do I have. Well, I have this x cubed up front. There's an x cubed. And when the things get large like this and I have a whole bunch of terms, I suggest crossing them out as you do them. That way you keep track of them, right? Because even I can get lost sometimes as I look at a whole bunch of terms and it looks scary. I'm trying to keep track of what I've added and subtracted and all in my head, and it's easier just to cross them out. All right, how many x squares do I have? Well, there's 2 terms. There's this one and this one. I have 2x squareds and 5x squareds. That gives me a total of 7x squareds. I'm going to cross them out because I've used them. Now let's look at the x's. I have -8x and a positive 10x. That gives me a positive 2x and then minus 40. And now I have placed my polynomial into standard form. Notice the degree is in fact 3 because I had 3 pieces to begin with and 3 roots. And according to the fundamental theorem, that's what it should be. Okay, let's do another one. I'm going to do a lot more. We need practice. We need lots and lots of practice. All right, you guys do this one. Let's do roots of 4 and 6 and -2. Let's try that one. You give this one a shot. please do it on your own. Practice multiplying all that stuff out, and then come back and see how you did. Okay, here we go. So I know that if I have a root of 4, I have a factor of negative 4. A root of 6 gives me x minus 6, and a root of negative 2 gives me x plus 2. All right, so let's multiply all this stuff out. Now you can multiply the first two out and then do the whole multiplying with the second thing. You can do that if you want to. I just find it's usually easier to think about it this way. It's just a personal preference. Okay, so I've got x minus 4. Now this is x squared minus 4x minus 12 when I multiply all that stuff out and simplify. And now I have x times all of these things. That gives me x to the third minus 4x squared minus 12x. And then I have negative 4 times all of those things. That's negative 4x squared plus 16x plus, 48. Now it's time to collect all my terms up. Let's change colors. So I have x cubed, done. X squareds, I have negative 4 and negative 4. That combines, not to give me 0, but further negative as a negative 8. That's negative 8x squared. Now, I have negative 12 and 16. That's like saying 16 minus 12. That gives me 4x. And then 48. And now, that's my standard form polynomial. Okay. Let's talk about a special case. Let's talk, now's a good time to do that. Let's talk about one with 0. Let's say one of the roots was 0, and negative 1, and say 7. Well, to get a root of 0, you could write x minus 0, and then, of course, x plus 1, and then x, x minus 7. You could do that. But what is x minus 0? Well, x minus 0 is just x, isn't it? So in the case that you have a root of 0, it would have just come from x, because x minus 0 is the same as x. So I'm going to rewrite this as that. Okay? So whenever you're given something like this and asked what the roots are, and you see an x by itself, the root is not 1. A lot of people say, well, the root's 1, right? There's always a 1. That's not how this works. A root of 1 would come from this, right? But that's not the same thing, is it? No. So the root, you think about it as there's nothing there, right? There's nothing here with it, and the number for nothing is 0. All right, anyway. So if you have something like this, how would I multiply all this out? Well, you leave the x alone and do this first. So employing my trick to do this quickly, I do x squared. That's going to be, plus, oh no, not plus, minus 6x, and then minus 7. And now when you get to this point, you're just going to distribute that x. You're just going to put that x through everything. So if I multiply everything in the parentheses by x, I get x cubed minus 6x squared minus 7x. Very simple. Okay. That also works with larger ones. Let's try that. You do this one. 0. Let's do negative 3, negative 4, and 1. All right. On your own, I want you to write a polynomial first in factored form with these roots, and then I would like for you to convert it to standard form. Go. Okay, here we go. Now I know if I have a root of 0, that came from x. I could write x minus 0, but that's pointless because lazy, right? And unnecessary. That's going to be plus 4, and then x minus 1. All right, so now I'm going to come down here, x plus 3. Just write those down. I'm going to, as I've been doing, I'm going to multiply these out. Right? So I get x squared plus 3x minus 4. Now, I'm going to distribute the x plus 3 into all of this stuff. That's how that's going to go. I'm still going to leave my x out front. Okay. So I have x cubed plus 3x squared minus 4x plus 3x squared plus 9x minus 12. Now, you can either go ahead and distribute the x throughout everything, or you can simplify the insides and then distribute the x. I suggest waiting till the very end. That's what I would do, but you do you. So I have x cubed plus 6x squared plus 5x minus 12. I think I got that right. And now, final step, I'm going to distribute that x throughout everything. So I have x to the fourth plus 6x cubed plus 5x squared minus 12x. And there is my standard form of a polynomial that has roots 0, -3, -4, and 1.